should I just begin? Yeah.
It's just 9. So to start, big final week here, John McGreevy, another graduate of the illustrious AdS.
Thank you, Joe. So hello, can you hear me? So my assignment here was to talk about applications of AdS-CFT to condensed matter physics. And I want to begin by assuring you that I'm taking my assignment very seriously. And although it may come to your attention as the discussion develops that I'm not really talking about like D-branes and black holes and the bulk and all these things as much as you might have thought I would. I really am taking my assignment seriously. And a comparison which I've been keeping in mind to explain, how it is that nevertheless I'm taking my assignment seriously is the following. It's maybe a little bit immodest, but so there's this famous quote from the great accelerator physicist Robert Wilson when he was at a congressional hearing about whether or not Fermilab would be funded, and one of the congressmen asked him, "Well, what good would it do for the national defense?" And his answer was, "It has nothing at all to do with the national with the defense of the country, except to make the country worth defending." And so to be very clear about what I mean, what I'm going to say in these lectures has, maybe not nothing at all, but maybe not that much to do with AdS-CFT, using AdS-CFT to study condensed matter physics, except to make condensed matter physics worth attacking. Okay, so that's my plan. We'll see if it works. Okay, and so let me begin with some context. So it's a very general context. The kinds of systems I'm going to be talking about, you might call them quantum systems with extensive degrees of freedom. And by extensive here, I mean the following picture. I guess it's best to draw a picture here. So here's a picture. And the picture you should have in mind. I'm drawing an unfortunately regular lattice, but that's not actually so important of a feature of what I'm saying. There's a bunch of patches of space. So each of these little things I want you to think of as a patch of space. And they have some location. So this is some direction x. And there's some set of quantum degrees of freedom associated to each patch of space. So here I'm telling you that the Hilbert space, calligraphic H, is a tensor product over these patches of space labeled x of some Hilbert space associated to each patch of space, which I'll call H sub x. It's finite dimensional. I will call the dimension of this local Hilbert space n squared for reasons that you'll see in a minute. And then we're going to couple them together with some Hamiltonian, which is some sum over those patches. Maybe it can involve some neighboring patches also. This is an eraser. That's not useful. Is there color? Let's see. I guess there's white and yellow. That'll work. Okay, so maybe one of these terms in the Hamiltonian involves several of these patches at once, but it's localized near one of these patches, and its support falls off rapidly. So it's a sum of terms like this, which are repeated in a pattern. They're not necessarily all the same, but I want you to think of this as a Hamiltonian motif. All right, so it's like one of these repeated patterns. It's not necessarily exactly the same. There can be development, but there aren't places in the world where really crazy things happen. That's an important assumption in what I'm going to say. And a useful thing to keep in mind about this picture, so this is not a very good depiction of what I'm going to say, but I want you to imagine the kinds of systems we're going to talk about as like a lawn made of sod. So that each of these little patches is like one of these chunks of grass rug, that people use when they're trying to make a lawn in a place where there shouldn't be a lawn. and this step of defining the system is spreading the sod on the ground, and this part of the system is coupling together the patches of sod to form a lawn. Okay, so this is a metaphor which I find useful. And so really what I'm saying, what I'm talking about, is a regulated quantum field theory. Like you might imagine that really we're interested in some continuum where this becomes small and the number of sites becomes large. But maybe not. We'll see. So, and I guess also it'll be important that there's an infrared regulator so that the total number of sites is finite and the total number of sites is this number over this number to some power, which is the number of dimensions. Okay, so that's the context. And this is very general, of course. It describes most of physics, maybe. And sometimes, given these ingredients, we can figure out what the system does. And usually when we can do that, it's because it's a bunch of harmonic oscillators, right? It may not be obvious how to find the right normal modes, how to find in which set of variables those harmonic oscillators will decouple from each other, but sometimes it's a bunch of harmonic oscillators. And I want to talk about what to do when that's not the case, and when is that not the case. And there are a few techniques besides finding normal modes and AdS-CFT. There are a few things in between, but we'll see what we can do. Okay, so maybe, so if it's not harmonic oscillators, then what do? Maybe we do AdS-CFT. And because AdS-CFT is a very powerful tool, it solves certain strongly coupled field theories in terms of classical. Sometimes in terms of some simple classical set of variables in one higher dimension. And all you need to do to understand what the field theory does is solve some simple wave equations. It's really wonderful when it works. And so we need to talk a little bit about when it works. Okay. So which systems can we try to solve this way? And I guess I might call this blackboard. Oh, I'm in the black hole. Okay. Yeah, it's a two-sided black hole. So this is limitations of classical holography. And I'm emphasizing this word classical because I don't want to impugn the value of AdS-CFT. It's a wonderful thing, but for the kind of wonderful fantasy scenario I was just describing, where you solve a strongly coupled condensed matter system just by solving a wave equation, it's important that the gravity theory is simple. It's important that you can just specify some boundary conditions and initial conditions and solve a differential equation. And so that's what I mean by classical here. And so when is it classical? And maybe I'm not going to review AdS-CFT here. I guess Joao did this already a few weeks ago. Yeah, so you guys all know this. So gravity is classical. No, gravity means large n squared, where n squared is that n squared up there. And so let me remind you why that's true. This is AdS-CFT is a wonderful example of the holographic principle in action, and as such it satisfies it. And so what I mean by this is, so the holographic principle, the sort of quantitative version of it, principle of quantum gravity, is the statement that the number, let's say the maximum entropy, let's say it this way, the area of the boundary in units of Planck mass to the right number of powers, so this is of quantum gravity, holographic principle of quantum gravity, it's like the only thing we know about quantum gravity maybe, is that its Hilbert space is not just a tensor product like this. I guess the most emphatic way I should say this is that in a theory of quantum gravity, the Hilbert space is not like that. That's the thing we know about it. But rather, the maximum entropy goes like, let's put a little twiddle, goes like the area of the boundary, whereas the maximum entropy of this kind of system goes like the volume. And so what do I mean by the maximum entropy? It's the maximum entropy state is if I just don't know anything at all, right? So that's the log of the total number of states is the biggest the entropy can be. What's the total number of states? Well, that's each site can have, okay, this is the dimension of, each site can have n squared, can be in n squared states, and there are how many states? There's, let's just say the number of sites here. All right, and so the log of that number is, did I get it wrong? Oh, okay. Here, let's just say number of states per site. Okay. This is inside the log. The total number.
Right, so the log on the right side, though, don't you want it times rather than raised to the power?
No, because
For the entropy.
the number. Sorry, my notation is bad. So this is the number of sites times the log of the number of states per site, right?
Yeah, times. It looked like an exponent there.
Sorry, that's my bad handwriting. Okay. And so, wait, what the heck just happened here? The number of sites is in the exponent. Yeah, okay. Right, so this is L over epsilon. That's the number of sites in each dimension. Yeah, sorry. Okay. Yeah, that's inside the log. So the number of sites is L over epsilon to the d times this number, which depends on the number of states per site. It's actually, I guess it's the log of n. Damn. It's even worse than I thought, huh? Yeah. Oh, okay. Sorry, I can make my point even more dramatically. This is e to the n squared. Yeah. Sorry. That was silly. Yeah. So this is the log of that number, which is n squared. There we go. Okay. Yeah. I was underselling my point there. All right. So this is the number of states per site this is the maximum entropy of one of these systems. And if we're going to equate that with the theory of gravity, we should set that equal to the area of the boundary of the space in which the gravity theory is living in Planck units. And okay, my handwriting gets worse as I get lower, so maybe I'll go over here. So let's compare that to the holographic answer. There we go. So AdS has a metric which looks like this. Over z squared. So z is some, here, okay, let me draw this picture so we can pretend I'm doing AdS CFT. This direction is z. Here's there are d of these spatial directions. This is a picture at fixed time, which is what we should do if we want to count degrees of freedom. So let's erase that guy. This is AdS. Oh, and there's some length I should write here, which let me call it r AdS squared. And okay, and then so what's the area of the boundary of this sort of Poincare upper half plane? Well, it's infinity, and that's because I didn't put in these regulators yet. So one regulator is easy. That's just this one, making these d spatial dimensions. There are d of these. Putting them in a box. And then the other one is a little more subtle, and I need you to remember things that Joao told you, which is that we stop the boundary at some distance from, we stop the space-time at some distance from the boundary, which is, this is z equals epsilon. I shouldn't write equals here because this is not a precise relation, but making this epsilon finite has the same purpose as making this epsilon finite. And it has the same outcome, too, because if we compute the area of the boundary, okay, I think it would be wrong for me to write the 4. This is an integral over fixed t and z equals epsilon of square root of g over 4g Newton. And okay, everybody can take the square root of that g. It's just z to the right power. It's and this is an integral over the spatial dimensions. And so this is L to the d from these integrals just go up to L. And this thing gets evaluated at epsilon. And so that's epsilon to the minus d. And then there's some bunch of powers of R AdS, which is the right number of powers, and a factor of g Newton. OK? Right, so that's, I just took this metric and found the volume element on a slice at fixed time and fixed z, and evaluated that area. And OK, so let's organize that. That's L over epsilon to the d that you recognize from over there, and times R AdS over g Newton to the d, R AdS to the d over g Newton. And so this is the same on both sides. And so if we want these things to be equal, we'd better set this thing equal to this thing. And so you see g Newton goes like 1 over n squared. OK? So small Newton's constant, which is the limit where the thing becomes classical, means that the number of degrees of freedom on each one of these patches of SOD is really ginormously large. Right? That is the control parameter, which makes the gravity theory classical. OK? Is everybody happy with that? My handwriting will get better, maybe. OK. And so, yeah, so e to the n squared is pretty big. It's actually, I can't believe I got that wrong, because it's, now I'm even sadder about the whole thing. Because, this is a strange situation to be in. It means that a system which has a classical gravity dual is sort of twice in the thermodynamic limit. Because, it has, if I take this L, the size of the space big, it puts it in the thermodynamic limit. Like, that's usually that's the way I reach the thermodynamic limit. I don't know about you. But this kind of system, even if L is finite, even if you put it in a tiny box and put it in your pocket, if you want to make gravity classical, you have to take this n large. And that means that even a small patch of it can be in the thermodynamic limit, which means that it can, for example, have sharp phase transitions, which maybe you heard about some of these already. They happen, for example, in studying the entanglement entropy of subregions. If you maybe. Did somebody talk about this? There's a picture that looks like this. There we go. Something like that. If you don't know what I mean, then never mind. But it's an example of a sharp phase transition of such a system, even if it's in finite volume, even if which is something that just shouldn't happen if the number of degrees of freedom at each side is finite, because the partition function is just a polynomial. OK, so that's weird, and it's a strange starting point for doing physics. And so the main conclusion that I draw from this discussion, both in this series of lectures and in my own life, is the following: is that if you want to know to which systems we might try to apply these techniques to learn something about condensed matter physics or about these kinds of SOD models, well, the situations where it will be most useful is when we're the most desperate, is when anything else that we might do to try to solve it is basically totally useless, and so we're willing to begin with this crazy approximation. All right, so yes, please.
I like what you said about the thermodynamic limit twice. It's sort of, I feel like when I'm really doing usual thermodynamic limits, I really need 10 to the 23 or whatever degrees of freedom.
Do you?
Or maybe 10 to the lot. Well, that was my first comment. My second comment is that when we talk about large N for something like a gauge theory, sometimes we try to apply it to N equals 3.
Yeah.
Which is pretty far away from the thermodynamic limit, and yet we hope it's still applicable to some reasonable accuracy.
Yeah, that's a good point. And so actually, it's an important distinction between trying to use these methods to study condensed matter physics and trying to use it to study the vacuum of gauge theory. Because in the vacuum, you're sort of tamping down all these degrees of freedom at each point, right? In the sense that you're putting them in their ground state and trying to leave them alone. Whereas we're going to be interested in putting some extensive amount of stuff, right? Where allowing the stuff at each point to get excited.
I think I could less easily get away with a smaller N in that case.
I think so. Wait, hold on. Are you saying that the classical gravity is good at N equals 3? I don't think you are.
No.
Yeah, you're saying that it's
I'm
that
just-
so a solution at large n of the vacuum of the gauge theory
of large n
says things
is
about
can be
finite. Yeah,
extended, yeah.
I agree. Yeah.
Can be
Okay.
useful because we may have a condensed matter system that is also maybe not n in the thermodynamic limit, but we might still hope to apply something.
Right. So the real point is not actually the value of n so much as this starting point forces an order of limits upon you. Right? When you do classical physics, you're taking n to infinity before anything else. For example, before any long time limit, before taking the low temperature limit. So it's really a question of the order in which the limits are taken. And this one pushes you into a certain corner. And those limits definitely do not commute. Right? Yeah. So I hope I've lowered your expectations sufficiently, and so that we can go on. And all right. So I have kind of a crazy plan. We'll see how it goes. The first item of business is, as you might expect, given what I just said, is to classify states of matter according to how desperate we are. To learn something about them using any kind of technique as opposed to some actually well-posed technique. So here's some attempt at a plan. So classification, no. Classification by desperation. And then I'm going to talk about gauge theory in condensed matter. So that is, how is it that you could get a system like that to be a gauge theory? So notice that probably everybody here, myself included, when I say gauge theory, you think, well, that means that the Hilbert space is defined in terms of some horrible thing with gauge redundancies, and there's gauge symmetries, and things are equivalent to other things. And okay, so notice that that's not at all the case here. Here I can be very clear about who the degrees of freedom are. There's one there, there's one there, there's one there. Nobody's equivalent to anybody else, right? So how can this be a gauge theory? That's a mystery I'd like to try to elucidate. Okay, and then I want to say something about entanglement renormalization, which is, I'm not going to be able to spell that word, okay, which is maybe the closest we've come to drawing that picture starting from there. And then maybe I'll say something about holography without gravity, which is kind of well, okay, we'll see. And then I want to talk about the example where we're the most desperate, which is Fermi surfaces. So specifically, I want to talk about killing Fermi surfaces, killing the quasi-particles at a Fermi surface in various ways. Okay, that's my plan. I have some notes that I've written, which I'll try to post to the wiki. That's what I'm supposed to do, right? Okay, I haven't done it yet. And I guess I'm going to be really bad about references, but there are references in the notes. And then finally, one exhortation I have, which is please ask me questions, because I don't know what you know. And maybe I'll say things that are totally obvious. Maybe I'll say things that are totally mystifying. I understand them. I don't know about you, right? Okay, so please take Oliver's lead, ask questions. All right, so here's the classification by level of desperation. Maybe I'll number these. Okay, 1, 2, 3, 5, and this is 1. Okay, so here's a good a quantity which correlates very well with our level of desperation is the following very coarse property of a state of matter, which is what degrees of freedom do we need to include to describe the system at the lowest energies? So that is, at energies below any interesting scales in the Hamiltonian, or so this Hamiltonian has some energies in it, and energies below that, below any of those scales, what degrees of freedom do we have to include? So, what degrees of freedom do we need to include at the lowest energies? And there are three possible answers to this question. which I guess maybe I'll give them letters. And the first possible answer is none. And the second possible answer is some. And then the third possible answer is a lot. Okay, and desperation increases in this direction. All right, that's my classification of states of matter. Okay, that's it. We can go home. Maybe I'll say a little more. To say a little more, let's assume translation invariance for a moment. So here, I drew this lovely, obviously perfectly periodic two-dimensional lattice, and maybe let's actually assume that I really do have translation invariance, discrete translation invariance for now. And so that means I can label the states by a momentum. Right? I guess it's actually, if it's only a discrete translation invariance, it's only a quasi-momentum. But within the Brillouin zone, I can pretend that it's really a momentum, and we can really use this as a label. And so when I say none, let's see. So here, what I mean by none is that the system has a gap, has an energy gap. So that is to say, delta E, which is the energy of the first excited state minus the energy of the ground state, is strictly positive. And that means that below that energy, there's just absolutely nothing. Right? It's just a theory of a single state. The Hilbert space is one-dimensional. Nothing to say. Well, it's not quite that simple. And so now I need to say what I mean. So this, the statement looks really innocent, but let me emphasize that I mean this even in the thermodynamic limit, and I mean even in the ordinary thermodynamic limit, even when L goes to infinity. Okay, so this is to be contrasted with the situation, for example, of the electromagnetic field in vacuum, where there are these waves, and the minimum wavelength that fits in the box is something like 1 over L, and the energy goes linearly with the wave number. Sorry, the minimum wave number that fits in the box is 1 over L. The energy goes linearly in the wave number, and so this is to be distinguished with that case where, which is this sum answer. So this is, well, I don't want to say massless particles, but let me say delta E goes like 1 over L to some power in this case. Right, so that's the case with photons. If you put photons in a box, the energy gap above the first excited state goes like 1 over L. That number is 1. And a way to think about this case is the following. It means that if I draw a picture of the momentum space and draw the spectrum of energies of the states of different momenta, in this case it looks like this. Right, so this is the picture of the values of the energy that a photon can have. And notice that it goes all the way down to 0. And at 0 momentum, there's a special point in momentum space, which is 0 momentum, where there's gapless degrees of freedom. And that's to be distinguished with this case, where the dispersion relation, if there is one, of the excitations, looks more like this. Right? So this is the delta E of which I speak, which is finite. And I guess the effect of having a finite box means that rather than lovely smooth curves, these are just isolated points. And in the thermodynamic limit, what happens is just that this fills it. OK. So the distinction I'm making between here and here is basically that here I mean a system with massive particles, and here I mean a system with massless particles. So these are the two cases I've spoken about so far. Now, more generally, the excitations, especially here, are not necessarily particles. So that is, you all know that there's a thing called a conformal field theory, where the spectrum of excitations instead has some kind of horrible power law singularity. Maybe it looks like this. Right? I don't know. I think you can get it to look like that. I don't know. Maybe that's forbidden. Okay, definitely you can get it to look like this, where there's some sort of cuspy thing there. So E goes like K to some awful number, which is how you get some awful number there. And the excitations are not necessarily particles. Okay, and so this is here I'm referring to the possibility that there can be CFT. Okay, and so this is a little bit harder than this case, right? To write an effective field theory for these degrees of freedom is a little bit harder, right? That's the study of conformal field theory. An effective field theory for these degrees of freedom is maybe not so bad, right? Because if you don't have this, if you have less than delta E worth of energy, you can't make anything propagate, right? So that's how hard could that be? But nevertheless, you can imagine that there is something interesting. You could imagine that there's okay. All right, I'll come back to the something interesting that can happen there in a minute. But then finally, I need to talk about the allot case. And the allot case happens in the following way. Here, the gapless excitations, the excitations with zero frequency, all happen at isolated points in momentum space. So just at k equals 0, maybe they're not always at k equals 0. In a lattice model, they could be at k equals pi or something. But just at isolated points. And that's to be distinguished from a case where the spectrum looks like this. Where all in here there's stuff. Okay, and so this point here is usually called 2kF. And how do you get this picture? Well, a way to get this picture is if you take free fermions and put a whole bunch of them in the same place. Period. Really. So you know, so let's think about the case where there is more than, say, there's 2 dimensions, and suppose that the problem is also rotation invariant. That's not so important, but it'll make it. It's nearly rotation invariant. It's easy to draw nearly rotation invariant things. Then we fill these levels of the fermions, and we can make cheap excitations by taking one of these guys, that guy there, and we can put it here, and then we make an excitation whose momentum above the ground state is that, right? That's somewhere here. We can make an excitation, we could put it here instead. Right? That's like here. And then the biggest momentum you can have for free is if you take one here from here, just below, and you put it all the way on the other side, just above. Right? So that's why it stops at 2kF, where I guess I should have said the radius of this little ball is the Fermi momentum, kF. Okay, and so in the case of free fermions, we understand this pretty well. In the case of systems which are adiabatically connected to free fermions, which is Landau Fermi liquid theory, we also understand it pretty well. But there are some other systems which have this kind of spectrum where there's this whole Fermi surface. I guess that's the important thing I need to say. There's this whole surface, whole locus in momentum space, which I'm making wiggly here, where there are gapless degrees of freedom. Right? So if I'm able to add a particle, I could just stick it there for free, no energy. It's just, it's a whole surface in momentum space of gapless degrees of freedom, in contrast to this case where it's just the gapless stuff is just at points. Okay, and so whereas in this case we kind of understand how to, we know a framework for thinking about conformal field theory in terms of the usual renormalization group. In this case, despite Joe's valiant efforts in 1992 and lots of other people's hard work, we still don't really have a framework for understanding non-Fermi liquids, which is the name for a system with a Fermi surface like this, but which is not described by free fermions, which is not adiabatically connected to free fermions. Okay, so this is the problem of non-Fermi liquids, which hopefully we'll come back to at the end there. Okay. Yeah. Okay. So the best example, actually, the one which most undisputably exists and is kind of, we understand a little bit about it, is the half-filled Landau level. So this is a compressible quantum Hall state, which is there's some good evidence that there's a Fermi surface, except, okay, there's one small catch, which is that actually it's an insulator, whereas, which is because of the degrees of freedom which are making up the Fermi surface aren't charged. But it's not a Fermi liquid based on the spectrum of excitations. This is, so one second. This is an example which is kind of understood theoretically and has some very clear experiments on its side. It's not the most famous example, The most famous example is the strange metal phase of cuprate superconductors, which, yeah, maybe I'll say more about it if I have to. But there, you can see the Fermi surface in angular resolve photo emission, but like nothing else about the Landau-Fermi liquid theory applies to it. Yeah. Yes, please. Yeah, it's a real life thing. Yeah. So unlike many of the things I'll talk about, wait, I thought you guys were string theorists. You're not supposed to ask that question. Yeah. So it's a real life thing. Yeah. Actually, I can draw a map. I can draw a map for you of where to find it. Here, I can draw it here. It's here. So this axis is temperature, and this axis is hold open. Okay. So you take a right at the antiferromagnet where the antiferromagnet ends, and then here's this annoying superconducting dome, which hides all the interesting stuff, and then you take a left, right? So it's here. Yeah. Okay, that's where the strange metal is. So this is sorry, I shouldn't be so glib. This is a sort of a cartoon of a phase diagram of a cuprate superconductor, and yeah, so these materials take their name from this part of the phase diagram because of the engineers, because humans care about being able to have superconductors at high temperatures. But from the point of view of physics, really all the interesting things are hidden behind there. They're visible at temperatures above the superconducting phase transition, and there's some evidence that if you suppress the superconductivity in a field, they continue a little bit lower. But basically, there's this annoying problem that we're forced to study this thing at this kind of finite temperature. All right, I'll say more about that here. Okay, I'm going to go through this list again one more time, a little more slowly. Okay, so I've been a little bit unfair to case A of systems with a gap, because except for a few brave souls, most of the papers that are posted to the archive in the condensed matter section in strongly correlated electrons or mesoscopic physics and Hall physics are either about free fermions or they're about gap systems. This is and this is just a statement about human courage. It's there's a lot of pressure to work on things that you have a chance of understanding, and things in this direction are a lot harder. But nevertheless, a lot of those things are quite interesting. So that's why I want to say a little more about that. Okay, so not all states of matter where there's an energy gap are the same as each other, and in fact, it's that case where we're the best at distinguishing them from each other, because we can make a very sharp notion of when they're different. So let me draw a picture. Okay, not in the book. Let me draw a picture of the space of couplings. Okay, I feel like this is the space of Hamiltonians of this kind of form that I wrote here. It's not just two-dimensional. Even if I restrict to some particular set of allowed interactions between my SOD molecules. But let me draw a two-dimensional slice. Then, okay, suppose A is an example of one of those gapped states of matter, and B is another one. What I mean by that statement is that they're separated by a wall in the space of couplings. So although I'm only drawing 2 dimensions in the space of couplings, this wall completely separates them, that it is real codimension 1 in the space of couplings, and on this wall is the place where the gap closes. Okay, so there's a very sharp notion of when two gap states of matter are different, right? It means that you can never get from here to here adiabatically, right? You could never vary these couplings in this Hamiltonian slowly enough to get from here to here without creating any excitations because the gap closes, right? So you all know the adiabatic theorem says that the speed at which you have to, the slowness with which you have to go is proportional to 1 over the gap. Okay, so this is a very sharp notion of when they're different. And so this guy here and this guy here, I don't know, so this one is A and this one is A prime. These guys are equivalent, right? So this is an equivalence relation that we've defined on this set space of gapped systems. And so you might like to know, well, what are the equivalence classes? Right, so that's a good question. You might be a little bit bothered by the idea that in order to tell, according to this definition, that this guy is really different from this guy, I don't know this guy here, you have to show that, in this quite large dimensional space of possible couplings, there's no way you could ever go from here to here without closing the gap, right? So the way to establish that these two things are different is not to exhaustively explore every possible path from here to here, right? That would be a bad idea. But rather, the good idea would be to find some kind of label, right? Some kind of label that you could associate to each of these states, which you know for sure can't change under smooth deformations, right? Something which is equal at each of the points on this side and equal at each of the points on this side, and is forced to jump when you cross this line, right? So these words I'm saying are the very definition of topology, and okay, and so this find topological labels on these equivalence classes. Okay, and so topology in this context can, it can arise in many different ways. It can arise because of the topology of the space the thing is living on, the topology of the many-body wave function, the topology of some band structure, and it's important to distinguish these things. And I'd like to spend some time unpacking them. Okay, so even in this case, which earlier I tried to convince you was boring, there's something to say because well, there can be, for example, one way in which topology can arise is it could be that the number of ground states, the number of these things that's here, depends on the topology of the space that you put the system on. That's something that can happen, and I'll show you that it can happen. And in that case, there is actually an interesting theory of those ground states, which is a topological field theory. Right? So in that case, it's not really a theory of nothing, it's a theory of the ground states. Okay. Another thing that could happen is, so for example, I guess I should mention that case is called topological order. The number of ground states depends on topology of space, right? Whether it's a 3-hole donut or a 4-hole donut, and notice that this is the reason that this satisfies my criterion is because this number of ground states is an integer, right? The number of ground states of a real physical system is an integer, and that integer for sure can't vary smoothly. But if the gap closes, then the number of ground states becomes ill-defined because they're all attached to these gapless modes, and the number of ground states can change by sucking some of those gapless modes into the ground state. Okay, and this is to be distinguished from another case, which is which is that you could imagine that even if the system is completely boring in the bulk, if you have just a chunk of it like this, if you somehow terminate your lawn with some kind of boundary, right, with some real boundary, here I was kind of imagining periodic boundary conditions, But you could imagine that if you make an interface between your lawn and, like, say, the sidewalk, that there could be something that happens there at the interface between those two things. And the reason that you might think this happens is, suppose A is your lawn and B is the sidewalk. Well, in order to get from here to here in space, so, okay, this is called edge modes. In order to get from, here's the picture of space, here's the sidewalk. Okay, sorry. So you have to vary some coupling, right? So one of these coordinates is G. Let's say this G is the coupling I'm varying to get from there to there. And you see G has to, G is going to vary from, I don't know, this is, actually let's make it vary a little more sharply than that. Whoa, that's messy. Okay. So suppose G does this. This is G sub A. This is G sub B. You see, in between, it has to cross this scary point where the gap would close if you used that Hamiltonian in the bulk. And so you might imagine that something interesting can happen there. So H sub G star, this is G star, this is G star, would be gapless. Okay, so you might imagine that something interesting has to happen there. All right. Okay. So now let me talk a little bit about expectations. There's something that kind of works in our favor. It's a sort of force in this direction when trying to make contact with reality. Let's see here. There's a force acting in the vertical direction of this axis of this picture, which we could call it, or maybe we could call it pessimism, which is that your basic expectation, for which if you're handed some random collection of these degrees of freedom and interactions, your basic expectation, if handed such a thing, should be this case. Should be the most boring case. And well, why is that? There's a bad reason and a good reason. The bad reason is just that if that weren't the case, then we wouldn't think it was boring. Right? If we encountered these things all the time, we would be jaded about them. The good reason, though, is that degeneracy in the spectrum of a Hamiltonian is something that requires a reason. Even a twofold degeneracy in the ground state of a Hamiltonian is something which is a priori not natural, in the sense that, suppose I have a Hamiltonian H0, and it has the property that it has two ground states, 1 and 2. Let me set the ground state energy to 0. Then, if I perturb this Hamiltonian by any operator, let's assume that it's local, so it's still within our space of possibilities, by any operator which mixes these two states, by any operator which has a matrix element in between these two states, then right, so then this perturbed Hamiltonian does not have that degeneracy. Right, this is, basically it's level repulsion that I'm talking about. So this is even for a twofold degeneracy. In order to have a gapless mode, you need to have like this sort of coordinated, degeneracy that depends on the wave number, which probably is because you left out some terms in the Hamiltonian. Now there are some better reasons why this can happen, which is why it does happen actually, and so it's worth trying to enumerate them. So let's do that. Okay. So the thing I'm trying to convey now is the following thing: gaplessness needs an explanation. And so what are some examples of an explanation? Well, the simplest one is if your system has a continuous global symmetry. Actually, let's talk about this example a little more. So, how could you enforce the idea that for every delta H you want to add, this vanishes? Well, one way to do it would be if you had some kind of symmetry which related these states, and you demand that your Hamiltonian preserves the symmetry. In that case, it can't act within the multiplet, and so all of this will be 0 for every Hamiltonian that preserves the symmetry. That is a toy example of Goldstone's theorem, which is the general reason that it's a general reason to have gaplessness, right? So this is broken, continuous, global symmetry. Okay, so that's a good reason. You all know what Goldstone's theorem is, right? Should we have a quiz?
I think it was derived in week 1.
Really?
I believe so, yes.
Who? By whom?
By Raphael.
Good. Ooh. Okay, all right. Yeah, good. Okay. The classical one. Ooh, that's not as good as the quantum one. Okay. Well, it's true even quantum mechanically, despite what you may hear.
He was doing word identities.
Oh, okay.
Yeah,
All right. Oh, I see. You didn't mean h bar equals 0. Okay, I see. All right, very good. All right, so let's regard that as understood, and I mean not just by us in this room, but also by humans. So this is I'm not saying that you're not humans. What I mean by this is, if your system is gapless for this reason, then it's kind of boring, right? It's boring in the sense that it's even though it's in this box, we shouldn't use AdS CFT to study it. That's what I mean, really. Okay. A second reason is sort of clear from that picture over there. If some giant hand takes a piece of chalk and tunes the parameters of the Hamiltonian so that it ends up on this wall of critical points where the gap closes, then it'll be gapless, right? So notice that this involves some external agency of some kind or another to carefully tune the parameters of the Hamiltonian. Okay, so maybe it was an experimenter carefully tuning some knob on the experiment. Maybe it was the anthropic principle carefully selecting for humans. Don't know. Okay, so these are examples. The third case is a little more dramatic. It's continuous, unbroken gauge invariance. Okay, so here what I mean is photons, or gauge bosons. Here, let's just say photons. Photons are massless particles. There's a good reason they can't get a mass because of gauge invariance, right? Actually, there's a paper from last December that claims that this is a special case of this, for the case of one-form symmetries. I don't understand this. Maybe somebody can explain it to me later. Yeah.
He didn't really talk about. He was here on it.
But he talked about supersymmetric gauge theories. Yeah. It's a shame because this is really interesting. Yeah. So maybe this is a special case. So this paper is by, I can't remember all the other authors. Seiberg, Kapustin, Willett, someone else. Gaiotto, really? Yeah, it must be Gaiotto. Does he have the record for most pages posted to the archive in a week?
We were discussing that last week. I think that must be the case.
I think so, yeah. Yeah, okay. Anyway, okay. Okay, this is... All right, so case 4 is a Fermi surface. So this is a really dramatic kind of gaplessness that we're explaining here. That's what I was explaining here. And I described this picture of how this particular state is gapless, and it has lots of gapless degrees of freedom, right? It's really floppy. But the thing I didn't explain, which is very important, is that not only is it gapless, but it's also stable. So this is, despite this thing I'm saying about if your Hamiltonian mixes the degenerate states, it'll lift the degeneracy. The reason, basically, is a kinematical reason. that the matrix elements of any local Hamiltonian between these degenerate states of those quasi-particles near the Fermi surface basically vanish. For kinematical reasons, basically because if you want to scatter some of these guys to some of these other guys, this is a terrible picture, basically the filled states in here get in the way. Let me leave it at that for now. Maybe we'll say more about that in the last section. And so here it's really a remarkable phenomenon, which I think whose full generality is not understood. Maybe we can think more about this. Okay. This is the only example in this table where the gapless degrees of freedom live at more than a point in momentum space. Okay, case 5 is the edge of a topological insulator. Oh, that's a word I should have said over there. So I'm making a distinction between these two things here. This case of topological order and this case of edge modes, which is the subject of topological insulators. And there's some evil people that try to conflate these two things and confuse us, but I think it's very important to keep these things distinct because they're very distinct. This can be realized by free fermions, and this cannot. Topological order is much more interesting. Okay. Case 6, so now we're getting into the dregs here, is a CFT with no relevant operators. Which I don't know if that's realized in anywhere. There are some examples in 2 dimensions, but I don't know if there's any physical realization of them. Sorry? No, that has a relevant operator. No, that's this case. Yeah. So here there's nothing to tune, is what I'm saying. Right? It's like a magical isolated beast. That's this case. True. Okay. Yeah, you're right. So that's a fair point. So this case may be realized for a reason, right? Which is this. Yeah. So I guess I was. Yeah. Fair enough. Okay, I agree. Let's put a question mark here. All right. So that's the end of my list. If anybody has any items to add to this list, I would very much like to know them. Yes, please.
Here you get to talk about these moduli space of inequivalent vacuum supersymmetry.
Okay, I'm trying to. Okay. That's this case. Then there's nothing gapless. Oh. Yes, you're right. Yeah, fair enough. Okay. Yeah, you're right, actually. Okay. Good. All right, so I'm reluctant to mess too much with my list, but okay. While we're in the dregs of the list here, I will add supersymmetry. And yeah, okay, I see. Unbroken chiral symmetry does prevent fermions from getting a mass. I'm trying to explain it away, but I think you're right. Okay, all right. Let's. That's a better reason than these. So that's 6, and then 7, and then 8, and then okay, good. I agree. Chiral symmetry. Good. Thank you. Anybody else? That's pretty good luck so far. I don't know. All right. Let's. Okay. So there are a few refinements of this list that I need to mention. The first one is by symmetry, which I guess I've already kind of said. Here, let's maybe put it in this box here. Refinement by symmetry. Which is suppose we restrict our attention to some subspace of the space of all Hamiltonians, which commute with some symmetry. So you tell me some symmetry group that you like and how it acts on that Hilbert space, and then we restrict our attention to only Hamiltonians which commute with that symmetry. And then there are two questions we can ask. Well, how does it act on H? So given demanding that G commutes with H, so G is some collection of generators of the symmetry, we can ask how does it act on H in the sense of what representations appear, does it act on one side at a time, and is it broken by the vacuum? So is there or is there not spontaneous symmetry breaking? And included in this entry here is some tricky business, which is the lattice version of anomalies, which has received a lot of attention in the condensed matter literature recently, and is the subject of is part of the subject of section 4 there, which maybe I'll talk about it. We'll see. I'm feeling kind of down on it right now. Okay, and then there's one more refinement, another quantity which is correlated with this axis, which is the amount of entanglement. So more entanglement means more desperation. And what I mean by entanglement here, I guess you've had 2 series of lectures about entanglement already, so maybe I don't even need to write down the formula for the von Neumann entropy. Is it true? You guys all know what that is? It's okay, yeah? Yes. All right, good. So here, but I need to specify which bipartition of the Hilbert space I am speaking of. And so here I mean the general situation we're going to consider, we're going to talk about it a lot, is we're going to have some erasing. Is oh, you know what? I'll try it here. Is some spatial bipartition where I pick some subregion of my system. I'll call it A, just like I called every other quantity, and it has some linear size R, and I will ask about the reduced density matrix of that subsystem in the ground state, and okay, and its dependence on this quantity R is a strong characterization of how much entanglement there is in the ground state. And in particular, for most of these cases, there is an area law, meaning that entanglement, the amount of entanglement, is dominated by this bit, the bit that is between just neighboring patches of SOD. And there's some interesting violations of that we'll talk about. Okay, but the important point that I want to say here is the reason to care about this entanglement for the purposes of this discussion is that if the degrees of freedom, if these degrees of freedom making up our SOD molecules were not entangled with each other, then we could use mean field theory. We could treat each SOD molecule on its own and think about its experience. Right? Think about it as living in a bath provided by the other SOD molecules, which is it just makes some effective action for the particular SOD molecule. We could treat it classically, basically, and that's called mean field theory. It means that the ground state is a product state, and that's to be contrasted with the case where the state of the full system is entangled. That means that it's not possible to speak of the state of a single system on its own, because it doesn't have a state on its own. It's entangled. That's what it means for it to be entangled. Okay, and so my point here is that more entanglement means mean field theory is more wrong, and it means that there's more room for interesting things to happen, and also more desperation. Okay. Yeah, so I guess, so mean field theory is sort of a solved problem from the point of view of the, experiment-free study of condensed matter physics that we're taking here. Though, of course, it's very interesting in the real world. Okay. All right, that's the end of my sweeping introduction. Does anybody have any sweeping questions? So we're going to get to work thinking about gauge theory and condensed matter. maybe it's a good time for erasing. So the first thing I want to do is give an attempt at a clear physics definition of topological order. And the physics definition is very simple, actually. It's just deconfined gauge theory. It means gauge theory. This is, I think, just redistributing the chalk. Yeah.
A few speakers have decided
To wet the
use of the water and
Yeah.
actually
Ooh.
use the sponge and then squeegee
Ooh.
it off. And Raphael did that, and that actually works if you're willing to do it. It makes it nice and clean, and you can write immediately after you squeegee it.
Squeegee.
There's
Oh, this is. All right, I see. I know this word, yes. Okay. I've been to the Bronx. Yeah, okay. All right, let's see. No? Squeegee. All right. Let's test this. Uh-oh. I broke the squeegee. All right, let's test this conjecture here. All right, that's pretty good. Okay, so equals deconfined, sort of necessarily emergent gauge theory. So this has the misfortune of being a physics definition, because now we need to understand what that is. But it has some very sharp consequences in the special case of gap systems. So notice I haven't restricted to the case. I haven't restricted this definition to the case of systems with a gap, but when there is a gap, it has some very sharp consequences, which are much better understood. Okay, so with a gap, this implies the following three closely interrelated things. Thing one is fractionalization of quantum numbers. Okay, so that is if, suppose our microscopic system has some symmetry, like say rotation invariance or some global symmetry or electric charge, that the microscopic constituents carry some representation of that symmetry, like say they're charge 1 electrons, then in a state with topological order, it is possible for the low energy excitations, the quasi-particle excitations, the excitations which are described by this dispersion curve here, to have quantum numbers which are fractions of the quantum numbers of the microscopic constituents. And this includes also so spin, charge, and also statistics. Statistics. Is that how you spell that word? Yeah. Which is, I guess, most dramatically possible in 2+1D. Though it is possible to turn bosons into fermions. Okay, and this I'll say more about this, but this generally comes with a further consequence, which is that topological ground state degeneracy I mentioned. Ground state degeneracy, which depends on the topology of space. So here I really mean you take the system and you put it on a Riemann surface of genus G, and the number of ground states depends on the genus. This sounds like a crazy thing to imagine trying to do, but there are actually some pretty realistic proposals to do it now by Mason Berkeshly and Xiaoling Qi. Now, they actually have some good reasons to do it besides just, because I want them, to be able to do. I want this to be realistic. Yeah. Okay. So why is this so I claim that this is actually a consequence of this one, and here's the idea for why that's true. So here's a picture of. Okay, I'll draw a boring one-hole donut, and this is a picture of space, and I'm drawing it embedded in this way rather than like that because I want to emphasize the conjugate nature of the two cycles. The two one cycles. So think about the following process. So imagine living on this donut is a system with topological order which has some fractional quasi-particles. And put it in its vacuum. And now imagine exciting the system a little bit by pair creating one of these quasi-particles and its antiparticle. Just in a little patch there. So that's some operator that I'm acting with. And now slowly drag one of them all the way around one of these things until it gets to there, and then annihilate them again. Okay, so this whole process is described by an operator, which has support on this curve that I've drawn here. And furthermore, there are good reasons to believe that the process puts you back in the space of ground states. So this defines some operator, which let me call it, I don't know, f sub x, if this direction is x. And I claim that this takes a ground state to another ground state, maybe not the same one. Maybe they could be the same ones. But now, here's the magic. We can take another kind of quasi-particle, maybe the same kind, maybe not, and create one and its antiparticle, and then move them around this other conjugate cycle. And the important property of these two cycles is that they intersect once at a point. And this defines another operator, which I don't know, let me call it f sub y. And the fact that these particles can have funny mutual statistics means that these two things don't commute. And they both take ground states to ground states. And in examples, there's some particular algebra, which is, you get some phase here or something like this. And so the ground states have to form an irreducible representation of this algebra, whatever it is. I haven't told you what it is. But in general, that can be more than one dimensional. Okay, so we'll talk about an example forthwith. And so the space of ground states necessarily is more than one dimensional because it has to form a representation of that algebra. So that's the sense in which this follows from this. And then finally, there's a third consequence, which also follows from, which one does it follow from? It follows from this, which is long-range entanglement. And what do I mean by that? It's a little bit hard to define this precisely. Actually, in section 3, I think it is, in the section about entanglement normalization, I can give a precise definition of what this is not. I can give a sharp definition of short-range entanglement. But basically, it means that if you look at the entanglement entropy of a region like this, there's a contribution which cares not just about the local physics near the boundary, so a contribution beyond just the area law term, which, for example, could be a term which is independent of the size. Actually, in this context, maybe this is a sharp statement. It says that the entanglement entropy of a subsystem like that has an area law term. That's r to the d minus 1. D is the number of space dimensions over some cutoff times some horrible non-universal coefficient, and then minus this golden, beautiful, extra constant contribution, which is called the topological entanglement entropy. And notice it's something which it's independent of r, is the important point. And let me show you that such a term cannot arise from entanglements just across the boundary. So this argument is due to Grover, Zhang, and Vishwanath. Okay, let us erase this. Okay, I'm going to try again. The trick seems to be to not destroy the tools. Oh, it's time to stop. Oh, I'm having so much fun. Okay, I'll erase this board, I'll explain that statement, and then I'll stop. Thank you for keeping me honest. All right. Okay. Yeah, I bet you could like rubber band them together. Okay, so let me explain that statement. Okay, the idea is if the system is short-range entangled, that is an antonym of long-range entanglement, then I must be able to account for the entanglement entropy of a subregion by adding up little bits. That is, I could cover the space in little balls. You know, maybe they can be bigger than, the balls can be bigger than the correlation length. And I should be able to get the whole thing from just adding up those little balls. And that means I should be able to write this as an integral over the boundary of A of some like entropy density functional, entanglement entropy density. Let's call it L dl. And the question is just what possible form can this have? And well, we have to be able to make it out of local quantities like the curvature of the shape of the boundary. And I think that's pretty much it. And so this has the form, in terms of the L, a constant bit. So this is some constant. It's like this is like the cosmological constant term. Then there's an extrinsic curvature term. And that has a coefficient, call that B. And then there's a, you can have a k squared. And I think basically all you can have is more powers of the extrinsic curvature. And I guess I've written in this, maybe, have I specified the 2 + 1 dimensions? I guess by writing dl I have. The argument isn't special to 2 + 1 dimensions so much. But then, okay, so then if we can do this integral. Okay, and the answer is, this gives the area law term. So L of dA is this is what I called R to the d minus 1, the length of the boundary, and this term is what would give a constant. This is B. I don't know. Let's call it B twiddle. It's proportional to B. The extrinsic curvature term is what would give a constant, and then this term gives something which falls off like the size. So this gives C twiddle over the length, and so on. Right, so this is like a derivative expansion of this fictional entropy density functional. And then the point is the following. In a pure state of the whole system, the entropy of A is equal to the entropy of its complement. Right, because the whole system is in a pure state. Yeah? Okay, yeah, some nodding? Okay, but now, in this calculation, there's this orientation, right? So I'm doing this integral with this. The extrinsic curvature comes with a sign, sign, SIG. And in the calculation of S of A bar, K becomes minus K. It's pretty cool because that means that in a pure state, this has to vanish, so this has to vanish. And so under this assumption, short range entangled implies gamma equals 0. So the only way to get this contribution is if there's some extra kind of entanglement, which is not just short-ranged. Okay, so that's what I mean by topological order. Those are some sharp consequences of it in the gapped case. And I guess next time we're going to start with an example, which is quantum Hall states. Okay. Maybe you could. Oh. Thank you. Yeah, more questions. More questions.
We'll have a question period also in the afternoon.
Oh, at what time?
Second afternoon slot. That works. Good. Yeah. Okay.
All right.
I have a tough question. As we said, you find the dimension of HX is EDN squared.
Oh, Yeah, so I was wrong about that initially. I mean, so I'm just naming n, but I wanted to make it match with the answer from AdS of t,
Oh, okay.
where the n squared is the number of colors
Okay,
of
yeah,
the
yeah.
gauge theory. Yeah, it kind of makes different.